what is actually happening when you have two aqueous solutions and you pour them together. Okay? Some things that we need to know. What exactly is a solution? A solution is a homogeneous mixture of two or more pure substances. What does homogeneous mixture mean? What is that called?
Uniform composition.
Uniform composition throughout. What's a pure substance?
Like water. Two molecular, two same substances, but I don't know.
What's a pure substance?
Is that an element?
That's an example of it.
Elemental molecule?
That's an example of it. But what is it?
Pure substance that can be separated.
Hasn't been separated.
That can be separated.
Hasn't changed.
It's made up of the same elements?
Throughout from
Same compound. You have the same thing throughout. Right? That's a pure substance. Here. Is this an example of a pure substance? Why is that? What's in there?
And water.
And water. Good. Okay? Pure substance is a sample of matter with a definite and constant composition. That simply means you have one thing in your solution. That's it. Right? Now, solvent of a solution. We need to know what's going on. Alright? Your solvent is simply, you have a solution, whichever is in the largest amount, that is your solvent. So let's take salt water for example. You have 8 ounces of water and 2 tablespoons of salt. Which one is your solvent?
Water.
Water is your solvent because it's in the largest amount. Solute of your solution. Your solute is any substance that's actually dissolved in your solvent. So i.e. it's whoever is in the least amount. That is your solvent. Solute, thank you. Right? You can have more than one solute in your solution. Your physical state of your solution. A solution can be solid, liquid, or gas. The state of your solution, the state of your solvent, will be the state of your solution. So if your solvent is a liquid, your solution is a liquid. If your solvent is a solid, your solution will be a solid. Do we get that? Okay. Take some questions. Identify the solvent and the solute in each of the following. White gold is a solid solution of 58.3% gold, 17% copper, 7.7% zinc, and 17% nickel.
So solvent will be the gold
Solvent will be the gold.
and solute will be
Zinc. Solid will be zinc and nickel. So I think the rest of them are solvent.
The rest of them, all of them that's remainder, the copper, zinc, and nickel, all of these are your solute.
So that means like a rest of solvent, everything is solute.
Yes.
The least amount.
Yes.
So can there be like more than one solvent?
No, you will always have
I have
one solvent.
right? Yeah.
Clean, dry air contains 78.1% nitrogen, 21% oxygen, and 0.9% argon.
Nitrogen. Solvent, solute is argon and oxygen.
There you go. Your solvent is your nitrogen, your solute is your oxygen, and your argon. Did we get that?
Yes.
Solubility. Solubility simply means how much of your solute can dissolve completely in a certain amount of your solvent. Alright? So now let's say we have 100 grams of water. In this 100 grams of water, it can hold comfortably to its maximum 10 grams of salt. Right? That will be, let's say if you add 12 grams of salt to the 100 grams of water, what do you think is going to happen?
We're going to be seeing the salt at the bottom.
You're going to see salt at the bottom because you have reached its capacity of the solubility. Did we get that? Soluble substances. Soluble substances are substances that dissolve to a significant extent. So if you add your salt, your 10 grams of salt to your 100 grams of water, everything is going to dissolve. That ultimately is a soluble substance. You have an insoluble substance, a substance that does not dissolve to a specific extent in your solvent. Let's say, for example, you have your water and you add sand to it. What's going to happen?
Doesn't dissolve.
It doesn't dissolve. So this is an insoluble substance. Do you get that? So then you have something called immiscible. Immiscible is described as when two solutions do not mix, or two substances do not mix. You ultimately get layers. Immiscible, you will always have layers forming. Here, oil and water. Oil and water would be considered an immiscible because they separate out into layers after a while. Do we get that? All right. Here's some questions. Use the term soluble, insoluble, or immiscible to describe the behavior of the following pairs of substances when they are shaken together. 25 milliliters of cooking oil and 25 milliliters of vinegar. The resulting solution mixture is cloudy and gradually separates into two layers. What?
Sorry, I had notes. So it says if it's cloudy, it's insoluble. And I heard cloudy, so I said insoluble before you said two layers.
There you go. I see. I understand. Okay? That's what I got too. Immiscible. 25 milliliters of water and 10 milliliters of rubbing alcohol. The resulting mixture is clear and colorless. That's what I got too. 25 milliliters of chloroform and 1 gram of roofing tar. The resulting mixture is clear but dark brown in color. Insoluble? Soluble?
Yeah, solid.
Ronnie said no. What do you think it is?
Soluble, I guess.
No, then no, I guess. You tell me what you think.
That was the majority vote, so.
No, I don't have no majority vote. I want to know what you think.
That's the soluble.
Why?
Okay, it mixes together.
Okay.
It's, mixture is clear.
But it's brown.
Color change.
The color change, yeah.
Yeah, you have a color change, so.
Soluble.
Soluble.
But why?
Because it dissolves. Yeah, it dissolves in water. So water is the solvent and the.
But we don't have water here.
How does it look like roofing tar?
Huh?
What's the color of roofing tar?
Black.
Black.
Clear.
We don't see each other like differently, so it's soluble. So it's
What do you mean you don't see each
like
other?
it's black and dark, like you can see it like you can give
Right, and some of them.
separate it by eyes, like you have to be with an external eye to separate it. It's already dissolved. That's why it's not.
What in here makes you think that it's actually dissolved?
It's like the colors mixed together. No, but
But if you put too much Kool-Aid in the thing, the Kool-Aid still was at the bottom, but the color will still change. So it's kind of, I don't know, it depends. I think I need more information. Is it at the bottom
All
or
the
no?
information is there.
Does that the dissolving means has to be clear or it doesn't?
The key word is clear.
So yeah,
So it's soluble.
it's soluble, yeah.
Okay? You have to look for the key word. You have to look for the key words though. You have to be able to explain it. Okay?
So whenever it
So-
says clear, that means soluble?
So if it is clear, means transparent. If you can see through it, that means everything is uniform. Right? If you have a precipitate, what are the two ways you can see a precipitate?
Cloudy.
It goes from what to
From clear to clear.
from clear to cloudy. And what else?
Yeah.
You have the solid that falls to the bottom. Okay? These are insoluble substances. Yes.
I have a question like insoluble. So he says it can be go to the bottom. So it will make a layer, right?
Not necessarily a layer, you can just have clumps.
But it's already we can see there's different part of the solution.
What do you mean? This one?
No, not like that. If I put a saw and sand on the water,
Mm-hmm.
so in the bottom you're gonna see a layer of the sand, right?
Yeah.
So it's also similar to immiscible. No, it's not make a layer.
Not necessarily.
This looks like that.
Because remember, immiscible, if you take a sample from the top, you are only going, let's say salt, oil and water. You're only going to get what?
Oil.
Oil. From the middle,
Water.
Oil and
oil
water.
and water from the bottom.
Sorry, water.
Water alone. Now, if you had sand in the water, you take a sample from the top, what you gonna get?
Water.
From the middle, what you gonna get?
Water.
From the bottom, what are you gonna get?
Water.
Sand and water. Okay, so these are not immiscible. It doesn't fit under immiscible.
Immiscible top and insoluble bottom.
I have a question.
Yeah.
If a mixture is heterogeneous, is it also immiscible?
Heterogeneous, yeah.
Yeah.
Whole lot.
Wait,
No?
not necessarily. Not necessarily. Me too.
Immiscible isn't the most cases the only liquids.
Yeah. Yes. Most of the time. Well, not necessarily, because you can have immiscible gases too.
For example.
So if you had argon and helium, okay? Which one is going to be, how are they going to situate themselves?
I think helium is going to be on the top.
Helium is going to be on top,
And argon is going to be
argon is going to be on the bottom. Why is that?
because argon is heavier than the helium.
There you go. Argon is heavier, so therefore it's going to sink.
So it depends on the weight of the compound.
Yes. Well, in that sense, but if you have oil and water, oils are long chain hydrocarbons, or not necessarily hydrocarbons, long chain fats. Okay? The molecular weight is much heavier than that of water, but it's their chemical properties that they surround themselves. Like they don't want to mix with the water. Okay? Okay, the solution process. Remember what I told you guys about the solvation? How, one marker. How if you have an ion, you have the water molecules will surround them. What does salt look like when you take it out of the little packets? Little crystals, right? So in these little crystals, they actually look like this. You have a lattice forming that interact with each other. Right? This is called what? What is it called? There are two processes.
Salvation.
No, not salvation.
Dissolve.
Who?
What was your question again?
Yeah.
What is this process called? We talked about it in lab.
Process of what?
Dissociation.
No? Who said it? It's Ronnie, loud and proud.
I heard it from her.
Whoever said it, tell me.
Dissociation.
Disassociation.
Oh, when the water, when the oxygen or whatever breaks from it.
No, not the oxygen breaks from it. You have, with what type of compounds will disassociate? Ionic compounds. Here in disassociation, you are going to break apart or separate the ions in the compound. This is exactly what's happening here. Each individual ion, so you can see the, see it. Is that better or no?
Yeah.
Awesome.
All the way dark?
All the way dark? Well, can you see?
No, turn one light on.
Hold on, I want to see if you can see my. Oh, you can kind of see it, sort of. Right? Each individual ion is being plucked out by the water and surrounded. This is what happens when you add an ionic compound to your solvent. Here, you have a molecular compound. Molecular compounds, your entire molecule will have charge separation. And your entire molecule is now going to be surrounded by the water. So the molecule itself stays intact. It does not break apart. The entire molecule is going to be solvated. And this is called dissolution. You get that?
That's an example.
So, what does sugar look like?
Crystal.
Same crystals, right? When you put sugar in your water, what happens to it? It dissolves, does not dissociate. Huh?
The sodium, the one that dissociates,
Not sodium, but sodium chloride or any type of ionic compound.
where the water just breaks apart the salt molecule.
Yes.
So
Alright.
ionic is dissociate.
Disassociate. Molecular is will dissolve.
Okay.
Did you say dissolution?
Same thing.
And you said it, the entire molecule becomes polarized?
No. In a molecular compound, you can have, when we get to polarity, you will learn more about that. But here you can see you have one side of the molecule has a negative charge, another side of the molecule has a positive charge. This has to do with polarity, and we'll see how that works in chapter 8. Okay?
You said it was dissolution and what?
Oh, wait, for the ionic compound?
Molecular.
Molecular compound, dissolution, or dissolve. Ionic compound, disassociate.
Dissolution and dissolve, you're saying it's the same as
Yes.
thing.
So again, there are reasons why your solute will not dissolve in your solvent, whatever the solvent is. First reason, the forces in between your solute particles are too strong to be overcome by the interactions of your solvent. So think about it as, back in high school, you got the jocks, they got their little clique. You got the debate team, they got their little clique, okay? It's like, one of them, the jocks want the debate team to come join them. But the debate team says, nah, B, we good, okay? We gonna stick to ourselves, all right? Solvent is all, come on, you're good at sports too. Come on down. But they're saying, than they are to the solute. Now we're going to flip it. You have the debate team, don't judge me. You have the debate team. The debate team wants to come join the jocks. But the jocks like, nah, B, y'all good. We good over here. Okay? This is what's happening. So ultimately, we can think about it as like dissolves like. Who does this remind us of? No. Who is this?
We shoot this double with this one.
Oh, that one.
Chromatography?
Chromatography and Junebug. Okay? Like dissolves like. If I am similar in attitude to you or similar in polarity to you, we can go together. Okay? If we are opposite, we can't rock. Do we get that? Polar solvents will dissolve polar or ionic solutes. Nonpolar solvents will dissolve nonpolar or non-ionic solutes. Do we get that?
So it's against the universal rule.
When we against?
Yeah, because it's always positive attract negative and negative attract positive. But here is positive to positive, negative.
But this is something different. Something different. All right, dissolution. The process by which a solute forms a solution in a solvent. Dissociation. This is mainly for soluble ionic compounds. Your soluble ionic compounds will break apart and separate into ions in water. Do you get that? An electrolyte. An electrolyte is a substance that will dissociate into its ions when it's dissolved in water. Knowing what we just went over, what can you tell me about electrolytes? What are they?
Ions.
Solvents?
Electrons.
They are an ionic compound. The only compounds that will dissolve or will dissociate into ions are ionic compounds. So therefore, an ionic compound, a soluble ionic compound, has to be an electrolyte. Non-electrolytes may dissolve in water, but they do not dissociate into ions. What can you tell me about non-electrolytes? They are molecular compounds or insoluble ionic compounds.
Hold up. Good.
All right? So again, what do we have here? What kind of process do we have here?
Breaking down the more iron.
Do we have dissolution or we have dissociation?
Yeah.
Disassociation.
It's
Sure.
ionic. Dissociation, yeah.
Dissociation. Each individual ion is being solvated. Do we get that?
No.
All right. So, what time we have? We got plenty of time? We got what lot of time? Okay? Electrolytes and non-electrolytes. Soluble ionic compounds tend to be electrolytes. If I specifically tell you that soluble ionic compounds are electrolytes, what can you deduce from that? If I specifically tell you, and I'm making mention of soluble ionic compounds are electrolytes, what can you tell me? What would be the opposite of that? No?
Insoluble or the other word you said before? Insoluble or
Molecular compounds. Tends to
Insoluble, tell me again?
insoluble molecular.
No molecular.
Insoluble ionic compounds tends to be non-electrolyte.
There you go. Insoluble
tend to be non-electrolytes or electrolytes?
Yeah, it's right there. This is how I need y'all to pay attention to what I'm talking about. Okay?
I
Insoluble,
thought I had to think. So I'm like,
insoluble ionic compounds are non-electrolytes. What do they form? If something is insoluble,
clouds.
a precipitate will be formed.
Yeah.
Alright? Molecular compounds tend to be non-electrolytes except for my acids and my bases. My strong acids, strong bases, they are electrolytes. Here you go. Ionic compounds, all of them, all soluble ionic compounds are strong electrolytes. We have none that are weak. The non-electrolytes will be your insoluble ionic compounds. The molecular compounds, strong acids, strong bases, will be strong electrolytes. When we say acids and bases and the fact that they are electrolytes, what are we talking about? What is going to happen to them? Acids and bases. I'm saying that acids and bases are strong electrolytes. What does that mean?
They're soluble.
Really solid.
No. Sorry, no. What are they going to do?
Give up
No.
electrons. Give up electrons.
In the area of that, but a little
Are
bit
you
more
talking about how
specific.
the water surrounds them? I'm talking about.
So what's going to happen to
They're
them?
not gonna.
They're gonna give electrons to the water.
They are gonna break apart because the water that's around it, no?
There you go. They're going to, what's the word called?
Disassociate.
They're going to dissociate into their ions. This is what electrolytes are. Okay? Now, what do you think a weak electrolyte would be for your acids and your bases?
You want to
No, just give me an explanation as to what they are. If a strong electrolyte will dissociate
They-
completely,
So they're insoluble?
not that they're insoluble, partial what?
They're gonna dissociate partially.
There you go, they're going to dissociate partially.
So the weak ones dissociate
Partially, the strong one dissociate completely, and the non-electrolytes, they will not dissociate at all.
Good question.
Yes.
So when we say that soluble ionic compound is associated with has a strong electron, does that mean like if we were to create a chemical equation that these would dissociate into ions instead of like say for instance what we just finished? Because like they're ionic compounds, like anything that includes like a polyatomic ion, right? Would that be considered an ionic compound?
What, polyatomic ion?
With another,
Like a what?
like a non-metal,
No.
that's not considered a polyatomic. I mean, that's not considered an ionic compound.
If you have a polyatomic ion bound to a non-metal, which you probably will never have, why will you never have that?
Because it's already an ionic.
No. Polyatomic ion with a non-metal. Why will this never happen?
Because it
They have the
doesn't
same
balance
charge.
each other out.
No?
They have the same charge.
They have the same charge.
Okay, so
Polyatomic ions
that's why
are
I'm saying
negative.
it doesn't balance in my head. That's what it means.
Well,
I'm like,
out your mouth, that's not what it
Why
means.
it wouldn't balance each other out if it was.
No, well,
Like say for instance, if I'm thinking in my head like it wouldn't be a positive to a negative.
okay.
So say for instance like potassium chlorate or something like that.
Okay.
If that were to be dissociated, it means it's going into its ions like K plus.
Yes.
Okay. In the chemical formula or equation.
The chemical equation.
Okay, chemical equation.
So that would ultimately help you figure out what the products will be. So you see how we did, what experiment was that? 4?
Yeah.
And how you found what the products are supposed to be?
Yeah.
By you first disassociated the ions, the compounds of your reactants into their ions. That now would help you figure out what the products are.
Okay.
That's what we're getting to right now.
So that means like the products on the other side of the
Yes.
arrow would have like a charge on it.
No,
No.
because once you have the new ions that are going to bound together, you're going to make the compound from this ion.
I guess I'll get some.
Yeah, we just
Yeah,
won't say
okay.
that right now. Okay? Now, a strong electrolyte will dissociate completely when it's dissolved in water. A weak electrolyte will dissociate partially when it's dissolved in water. If you look here, little science experiment, okay? What exactly is supposed to happen here? No spark. You're trying to light the bulb, okay? How exactly do you need to light the bulb? What needs to be happening in here with your anode and the cathode?
Flow of electrons.
You need a flow of electrons. Here, we just have pure water. You get no light. Why?
No electrons.
But why? What is water?
Pure substance.
No, not that it's a pure substance.
Molecular compound.
It's a molecular compound. Molecular compounds will not dissociate into ions. For right now, water does not dissociate into ions. For right now.
Regular wood, like pure.
Just water, period.
Oh.
Okay? When you get to 202, we're going to see something different. Okay?
I thought if it's like regular, like say for instance any water that has interference with any type of other, I guess. Like say for instance it was like bath water. You think it's all water, but it's not water.
Well, the water that comes out of the tap is not pure water.
Right. That's what I'm saying.
It is all kind of minerals in there and fun stuff.
So if it's pure water, it's definitely not.
No, if it's water, if it's water itself, you are not going to have, you're not going to have
It's not
any
there.
ions in there. Okay? So now here, we take your sucrose, table sugar, and you pour it into your water. Still no light. Why?
Because water just dissolves, so it's not.
But water
Not
dissolves
the
what?
water, the sugar. The sugar
The
dissolves.
sugar dissolves.
So it's not like the thing, the word. There's no electrolyte.
But
Non-
it's a molecular compound, so therefore you have no ions forming when it dissolves. But looky here. When you have your sodium chloride, your table salt, you get a big old nice light bulb.
Because it disassociates.
Because it disassociates into their ions. This is an ionic compound, so therefore you now have that flow of electrons to make your bulb light. Keith.
What's the molecular formula for glucose? What, sugar?
Sugar and glucose are two different things.
Yeah.
Sucrose, table sugar,
Yeah.
C12, H22O11. Glucose, C6, H12, O6. Sucrose is a combination of glucose and fructose. And they make sucrose.
How long does that stay like typical?
It depends
And how much sugar you add, or?
how much sugar you had. Sugar
Nah,
like that.
salt. I'm sorry, salt.
How much salt you have in there. Because remember, your electrons are going into the bulb. Okay? If you only have a little tiny, itty bitty little bit of electrons going in there, add a little bit of salt, you're going to get the light for a certain amount of time. But if you keep pouring salt in there, you're going to get the light for a long time. Okay? Again, electrolytes, non-electrolytes, strong acids, strong bases, soluble ionic compounds. These are all electrolytes. My strong acids, hydrochloric acid, you must know and memorize these. Hydrochloric acid, hydrobromic acid, strong acid, hydroiodic acid, chloric acid, perchloric acid, nitric acid, and sulfuric acid. These are all your strong acids. Your strong bases, they are the hydroxides of your group 1 elements. Your hydroxides of your heavy group 2 elements. That's them down. Do we get that? Yes, you must memorize these because they don't give you this on the exams. You know, writing it down helps, right? Helps you retain the memory. Putting that out there. Yes.
That thing you showed last slide for light a light bulb, is that anything that needs electricity to conduct?
What do you think electrons are?
Since we're talking about it, because there's like light energy produced. Well, decomposition is heat energy, no, as the
You mean combustion?
combustion.
Combustion, you have energy released in two forms, form of light or the form of heat.
So is that combustion in the electron?
Well, not necessarily. You just have the electrons moving up to a higher energy state, and when it comes back down, it's releasing that light.